In this video, we're going to continue our gambling addiction by looking at a different version of this sort of gambling problem where we will perform some random task and then we will potentially keep playing depending on what happens. So in this case, like our previous one, we have a repeat until loop here, and now our lose condition is if we roll a 6 on a 6-sided die, we're going to quit, and otherwise we'll keep going. So let x equal the number of rolls that are not a 6. So again, this is just trying to compute the number of times that we're going to go through that loop. And exactly like our previous example, we are going to say that the runtime is, the expected runtime that is equal to constant from always running that bit of code the first time, plus the constant times the expected value of that variable we have defined. And we're going to compute that variable the same way as we did before. We want to know what is the likelihood that it is greater than or equal to a particular value. So we have C plus the sum from I equals 1 to infinity of the probability that x is greater than or equal to I. And just like we did last time, let's try and understand that. What is the probability that our die rolls a 6? If it's fair, it's 1/6, or if you're me playing Dungeons and Dragons, that's about a 0% chance. We have probability that D is not equal to 6, which is the one we're more interested in, is 5/6. So the probability that x is greater than or equal to 1, the probability that I roll at least one thing that is not a 6, well, that's 5/6. I have 5 options on my first roll out of 6 possibilities. So the probability that x is greater than or equal to 2, well, that's rolling a 1, 2, 3, 4, 5, or 6 times that happening again. And those are independent events, as I said before. The probability that x is greater than or equal to I, just looking at what we have there, should be 5/6 to the I. So let's use that over here while computing our expected time. The expected time is equal to C plus C times the sum from I equals 1 to infinity of the probability that x is greater than or equal to I, we said was 5/6 to the I. And the formula I used last time I will use here again. The infinite geometric series, if it does not start at 0, the formula is that you write the first term of that series, so I have 5/6 to the 1, over 1 minus the common ratio of 5/6. And now let's simplify that just so we can see what actually happens. This is equal to C plus C times the denominator there is 1/6. That simplifies into a nice way of 6C, because that second term is 5C. And this might be what you expect. You'd expect it to take about 6 times through. And just like our previous example, the expected time is in theta of 1. Even though, as before, the worst case runtime here is going to be infinite. So, why is this useful, you might ask? We will see another example of this, but I will mention it now. This sort of analysis shows up with things like hash tables, which we will see very shortly. So it's not just some sort of abstract problem with this silly little casino example. It will show up later when we're analyzing things in the future.